Okay, so what I want to do in this lecture is to talk about models of stochastic programming and in particular issues that come up in modeling and how you structure these problems. And at the end, I'll particularly talk about how you make sure that you eliminate problems that can make a model sort of invalid. So I'll talk about what it means to be invalid. But what I'll begin by doing is I'll give you another example of a stochastic program, this time with multiple stages. Here it'll be 3. And what I wanted to illustrate is another feature of stochastic programs, that they allow you to make things depend on the revelation of information and when information occurs. So we kind of had, the first example was to show you that solutions can depend on, or solutions can differ depending on how you represent when those outcomes occur in the future. And this is going to illustrate that your decision can actually be adapted in time to things that happen in the future. So I'll show you how that works. And this also will illustrate non-anticipativity. So I'll use that to sort of illustrate that, which is a concept in stochastic programming that we use a lot. Then I have another example which is based on vehicle routing, so like how you would route vehicles through a network. And what I'm going to use that to illustrate is where the model has more value than information. So like in the last example I had, the information value was worth more than the model. In this one, the model will be worth more than the information. And then I'll talk about modeling from an overall perspective. And then, like I said, issues that can invalidate a model. So one is that a model might unintentionally include arbitrage, or include the opportunity to make money when there really isn't something there. So I'll talk about making models consistent and avoiding arbitrage. That'll be the last part. Okay, so here's my my first example. So this is financial planning. So we want to accumulate a certain amount, let's say to pay for something, like pay for a house, pay for tuition. So we want to accumulate that certain amount. So we want to get to G in our wealth, and we want to do it in a certain number of years. So Y years. What I'm going to assume is that it's worth more to get to G than it is to have wealth beyond G. So if I can get to G, that will be very good. I will have been able to save enough to buy a house. So I'm trying to save money to buy a house. Once I get enough, then I say, okay, now I can buy a house, and that's great. But if I have more money than necessary to buy a house, that's nice, but it's not worth as much as getting money to buy the house. So I'm just saying that I have like a goal. And anything short of that goal is negative to me. So my goal is to get the house. I'm just going to say I have a certain utility to get to the house. If I don't get there, then I'm penalized for it. That's the way I'm going to think about it. Okay, so I'm trying to save this money, and I want to get enough to get to be able to buy the house. So anything below that, that's going to be a penalty. I get some reward for being above it, but that's not worth as much. So this is the form of a concave, because I'm maximizing here, a concave utility. It's has a higher slope up until this point G, and then the slope becomes lower after that. Now it's piecewise linear because it's linear up until this point, and then linear with a different slope beyond that. So what I'm going to assume is that I start with a certain amount of money right now, W0. So I start with a given wealth, and then I make investments over time. So I take the money that I have, I invest in different assets. Those assets have different returns, and then I try to get to this. I want to get to that benchmark. So I want to get to that target. Okay, so the way this is going to work is that I'll invest, I'll get to observe the returns, and then I'll get to reinvest after I make those observations, and then I'll observe another set of returns. I'll get to reinvest after I observe those, and then I'll observe another set of returns, and then I'll calculate either the reward that I get for being above the goal, or any penalty if I'm below the goal. Okay, so this is the form of the problem. Okay, so that creates this is like a decision tree where I make decisions in these boxes, and then there's some random outcome that happens after those that brings me forward through time. Okay, so I'll have this pattern of act, observe, act, observe, act, observe. Okay, so that's the framework of this model. Okay, now right. X1 is initial investment, and then X2 will be after I make some observations. Yeah, it's either gone up or gone down. Yeah. So I get to observe what the market returns are, and then I make another decision, then I observe, make another decision. Okay, now, so here's where I'm going to set things up. I'm going to assume that each one of these paths, like if I take a path like this, that's a given scenario. So this would be like one scenario, this would be another scenario like that. So there are a number of different scenarios. The way you could think about making decisions is, it's as if I made a decision on each of those scenarios. Like I could have a decision, this would be like the wait and see decision, where I know what the returns are. Well, at this point, I'm going to invest until I reach time is y. So I reach that time, and then I either hit G or I don't. Yeah, and then I'll see. Okay, so each of these is a different set of scenarios. So you could make it with your decisions all depending on the scenario, but then you constrain the decisions such that they're the same if you have the same information. So I have a set of scenarios. So they're like, here there would be 8 scenarios, but the decisions of all 8 scenarios have to be the same at the beginning. And I can put that in as a constraint instead of just saying, okay, I make one decision at the beginning. Okay, so the way I'll set it up is as constraints. So I'll say each of these is a different scenario. So I'm indicating the scenarios by sigma. So the little sigmas are in big sigma. Big sigma is the set of all scenarios. Each of those scenarios has a probability. So this is the probability of each path, each sample path of all those possible outcomes. Yeah, the product of each of the different outcomes, yeah. So that's the probability of the entire path. I group the paths together if they have the same information. So like if at time t, all the scenarios that have the same information in group 1, and then there are ST groups at time t. So I group the scenarios together if they have the same information. And now my multi-stage stochastic nonlinear program in this case is I maximize the sum over the scenarios, the probability of each scenario, and then the utility that I get at the very end, that's here by U, for the wealth that I have in each scenario at time, here I have capital T. So T is the last time period. So this is my expected value at the very last time period. And now the dynamics are, at the beginning, I invest everything. So this is X is, I invest in asset K, an amount X, in asset K at time 1 under scenario sigma. The sum of the investments over all the assets is equal to my wealth. So I take my wealth and I invest it into different assets. At each time period, those assets have a return R. So I take each of these assets at time, let's say t minus 1 here. At time t minus 1, whatever I had invested in, it had a return of each of those assets at time t minus 1 under each scenario. And then, yeah, I could do it either way, but I indicated it here by t minus 1. But I'm thinking of it as at the beginning of time t, I haven't seen the return yet, and then I get the return. So I get the return after I make the investment. So in other words, I make the investment in time 1, and then I get the return for time 1. So I get the return from each of these assets, but then I reinvest it. So I have the return, and then how much I had invested, and then I get to reinvest it in the assets for the next time period. So like at time period 2, I would have the return in time 1. So if t is 2, then this would be what I had invested it at time 1, what my return was in time 1, and then I reinvest that at time t, at time 2. And that depends on the sigma. And yeah. Well, I'm going to spend all of it, but some of it might be cash. Some might just be sitting. Right. Yeah. But one of the securities might be cash. It might just be that I don't invest in anything. Just keep it in cash.
So this X1 is only a part of W0.
It's a part of W0. Yeah. Well. So the first constraint is really like it's like x 1 t equals 1. So that might be my stock, and then x. Here it's k is first. So this is 2, 1, again, t equals 1. And this might be bond or cash. And that's equal to my wealth. So part of it is in stock, and then part of it is in bond. Oh, K is, so this is the K. This is the asset. K equals 1, 2. That's the asset. Okay, so so I invest in each of these assets, and then I reinvest, and then at the end I collect it into my final wealth. And that's my final wealth in the very last time period. Yeah, so the last time period is going to look like X 1. This is T minus 1. Or, T minus 1. This was sigma equals 1. This is sigma. This is T minus 1, sigma plus X2, T minus 1. Sigma is equal to my wealth. All right, this is the return. So this would be the return of asset 1, T minus 1 and sigma. This is the return of asset 2, T minus 1, and sigma, like that. Okay. So what I've done is I separated it out for each of those sample paths, but then I have a constraint, and the constraint says if two scenarios, sigma prime here and sigma, are in the same group, in other words, if they have the same information at time t, then they have to have the same investments. So that says the decision cannot depend on the future, or the decision cannot anticipate the future. So we call that non-anticipativity, that the decision cannot depend on the future. And that's a way to write as a constraint that that my decisions are only adapted to the actual information. They can't use information that hasn't been revealed yet. Okay, I'll show that in this diagram here. So what I had before was a tree like this, where I was making decisions at each node of this tree, and then there were possible outcomes of those decisions at each of those nodes. So I had 8 scenarios for the outcomes and decisions at each one of these different points in time. So these would be like, how much do I invest in stock and bonds, stock versus bonds? How much do I invest in this point, stock versus bonds? How much do I invest here? And then I had separate decisions along the tree. What I've done is I've taken each of these paths, so there are 8 different paths that are possible, taken each of those paths and written them separately. But then I've described the condition that everything here has to have the same decision if they have the same information. I've taken all the things that are in the same information set and said all of them have to be equal to each other. So these 8 scenarios that are in this set that shares the same information, there's only one set at the very beginning, they all share the same information. All of those decisions have to be the same. At time period 2, there are 2 sets, so there are these 2. So all 4 of these paths have to have the same decision at this point. All 4 of these paths have to have the same decision at this point. So all of these together have to have the same decisions. And then at time period 3, all of these pairs have to have the same decision. And then each of them can be different in the very last period. Okay, so I've taken the tree and written it as 8 different paths or 8 different scenarios that are all linked by these constraints. So the constraints give me the information structure. So I take the information structure that was given here in the tree and I put it into the constraints.
Final
Yeah, these are the final decisions. Yeah.
And plus this S1 on this also need to first one, those 8 would be the final decision.
Right. 8 are the final decisions.
Okay, now
Yeah. Yeah. So the eight just have my final decisions. But along each path, then I have these constraints. Now, the reason why you might like to do this is because now I can relax the constraints associated with the information. So I get a way in which I might be able to solve this problem by relaxing the information constraints. And then I can say, I want to do this in 15 years. All right, so I want to get 15 years, so I want to be able to save, let's say, $80,000. I'm going to do it in 3 different decision points. So I'm going to say there are 3 points at which I decide to reallocate my investment. So every 5 years, I'm going to reallocate the investment. So I'll make 3 sets of decisions, 1 now, 1 in 5, 1 in 10 years. So I'll make those decisions across just stock or bonds. So I'll either take stock or I take bonds. So you could think of bonds as kind of like cash. And let's say the scenarios are this. The scenarios are stocks go up 25%, bonds go up 14%, or stocks only go up 6% while bonds go up 12%. In other words, stocks either go up more or less relative to bonds. And so these are the returns that we have for each of these 5-year periods, and I want to get to this 80,000 goal. Okay, so if I solve that, if I solve the linear program, so the linear program is this, this framework here, because it's a linear program because I end up with, this is piecewise linear, so even though it's the form of a nonlinear program, I can write it as linear program by making this linear on each of the different pieces. Okay, so I solve that problem, and I get a decision where, again, the constraint says that each of the scenarios, for each of the scenarios, I make the same decision in the very first period. So I started off with, it doesn't say up here, but I start off, I think, with 55,000. Okay, so I start off with a given amount, 55,000, and I split it up between stock. It's about 80% in stock and 20% in bonds. So in the very first period, in other words, for all scenarios 1 through 8, I put this amount in stock, this amount in bonds. In the second period, I put, now this is for all the scenarios where stocks went up a lot. So 1 through 4, stocks went up. This is where stocks went up a lot. If stocks went up a lot, I put even more in stocks in that second period. If stocks underperformed bonds, then I put less in stocks in that second period. So in scenarios 5 through 8, I do something different. Okay, so this one, I become more stock invested here, and I become less stock invested in this scenario. And then in the last set of scenarios, so I have these 2 scenarios where I make a set of decisions, these 2 where I make completely different decisions. So this scenario is where stocks have been up a lot. Well, at this point, I already have enough. I already have 80,000. I'm already over 80,000. So because I'm already over 80,000, I'm not worried about risk. Because I'm not worried about risk, I know that I've already made my goal. I invest everything in the risky asset. So I invest everything towards stock. In the case where I'm somewhat in between, where I have, I'm uncertain as to whether I'll be able to meet my goal. But you can see I'm more likely to be able to meet the goal all the time if I sort of act conservatively. If I put everything in bonds, because I'm guaranteed of getting 12%. So if I put everything in bonds, I'm guaranteed that 12%, I'm guaranteed to make my goal. So because I'm guaranteed to make the goal in both of these scenarios, I decide I'll just put everything into the bond, and I'll be able to make my goal because I get this, the minimum return is better. Now here's the one that's sort of different. If stocks have been performing poorly, then the only way, in these two scenarios, the only way I can make my goal is to put everything into stock. Because the only way I can make my goal is if I get the high return. So if I'm so far below that I really have to gamble to get to the high return, I decide to do that. So I have this, that I become very aggressive in one case, and then as stocks perform less, I become more conservative, but then once they're performing sort of poorly, I do the exact opposite kind of reaction. Okay, so the stochastic program gives us a feature, again, which we won't see in a deterministic model, but we also won't see this in a static model like the traditional mean variance portfolio optimization. So if I just use a single period portfolio model, I won't see this kind of behavior. This behavior of I can act aggressively now because I know that I can change my actions in the future. And then I'll change my actions in the future depending on the outcome, and I may end up acting aggressively again, or I may end up being conservative. So I get to adapt in the future. So it allows me to anticipate that adaptation, which I wouldn't get in like a standard mean variance kind of model. Okay, so this is an example of asset liability management. Deciding how to allocate assets over time, and often what liabilities to perform. But this is kind of investment of trillions of dollars. What stochastic programming allows you to do is to include this adaptation. So that's one of the things that it allows. That's something that these models that only look at kind of static versions of investment are not going to be able to capture. And the other thing is it can capture all sorts of sort of specific things like transaction costs. So traditional models are like this mean variance where you just take the mean and then subtract off something related to the variance. They often don't consider that you're going to change things in the future, and they also don't consider things like transaction fees, or that you can lock in your gains, like in that case where you realize if you switch to bonds, you'll be able to lock in your position. You could try other things like dynamic extensions of this, but they end up being just fixed proportion. You always have a fixed proportion in your stock or your bonds. Yeah, there's some other things, but stochastic program is what we're going to focus on. What happens in the static portfolio model? Well, the static portfolio model is that you find an efficient frontier. You find the minimum risk for a given return. You choose a portfolio that minimizes risk for a given return, but it's always just a single period allocation. So you're just looking at one period at a time and then trying to decide what you should do for that single period. So you would minimize something like, if this is your covariance matrix, this would be like the overall variance of the portfolio. So you would minimize the overall variance of the portfolio, which is this quadratic program. So it's just x transpose times the covariance matrix times x, and then set a target. So you would set this is your expected return for each of the assets, You would set such the expected return times each of the assets, sum together equals whatever your target return is, and you use up your investment. Just E is the vector of ones. So you use up the investment, and it might be non-negative, or you might allow negative positions, but you would optimize by minimizing the variance here. Okay, so what that will say is for a given amount of return that you want to receive, you want to set up whatever will give you the minimum risk. So in this investment problem here, you would say, okay, I want to achieve this goal, that $80,000 goal. I would find out what return do I need in order to achieve that $80,000 goal, and then what portfolio is going to give me the minimum risk that achieves that return. Okay, so you would find the percentages that would invest, and you would maintain that percentage over time. You might rebalance, but you wouldn't be explicitly considering what might happen in the future, like how much would you have to pay to rebalance in the future, or if things were performing well, you wouldn't be anticipating that there would be times at which you'd be able to lock yourself in. You'd be able to say, oh, I already have enough to reach my goal, so I shouldn't take any more risk. So and in reality, you would want to be able to lock those gains in, but this model is going to suggest that you just maintain that given position over time. So that would be that you always hold a given amount in your stock and bonds. If I wanted to get a 15% return, I would have 80% in stock. A 40% return, I would have, or a 14% return, I would have 40% in stock. It turns out that there's no way, any way I do this, this is sort of similar to my last example. Any static version of this model is never going to get you to the goal more than 50% of the time. So there's no way, if you continue to take these kind of risks, if you always invest 80% in bonds or always invest 40% in stock, you'll never get more than 50% of the time reaching the target. Whereas the stochastic program, by being able to adapt when I'm ahead, oh, I'm not going to take any more risk. When I'm below, I'm going to take even more risk because I want to get ahead. So that nature of the stochastic problem or stochastic program to be able to adapt to your current condition is completely different from this outcome here. So in the stochastic program, you achieve it 7/8 of the time, 87.5% of the time. So it's able to do something that these static models can never do. So a stochastic program has characteristics that no deterministic program has. It also has characteristics that no static or single period problem can reproduce. So the portfolio problems that are based on just a single period return, which often people think of, I can just look at what returns I get over a single period, and if I reproduce that, that could be optimal. But that's not necessarily true. That, in this case, you'll never be able to get any more than 50% of the time. Okay, so the other thing with a stochastic program is that what can it do? It can include transaction costs, so I could include transaction, if there were costs to rebalance in any of these time periods, I could include those as well. I could include tax. So one thing that's often not included in these models is to include the tax that you might have to pay on returns. Stochastic program can include tax as well. It creates maybe larger models, but the stochastic program, its biggest benefit is that it's comprehensive. It allows you to include all of these other things that don't occur when you just look at like the mean variance portfolio model. Okay, so in this model, The dynamic model allows for changing the policy to changing conditions. You're able to lock in your gains. No single period model can reproduce that. And so the structure of the optimal policy solution. So that first example was the nature of the solution and having the two different places in which the tight constraints occur. That can never be reproduced by a deterministic model. The locking in gains or adapting can never be reproduced by a static model that just looks at a single period at a time. Okay. Now I'll show another example, and this is to illustrate the nature of these models. So let's say that we're routing a truck to deliver gasoline to different places. So I have like 4 different gasoline stations that I have to deliver to. And I start from the depot here. So I go from the depot and I can go out to each of these different locations, each of the different gasoline stations, and deliver gasoline to them. And let's say I've heard how much is left in station A, B, and D. So I know exactly how much I need to fill them, but I don't know how much I need at C. So either I haven't heard back from them, or maybe their machine isn't registering how much is left in their tank. So I don't know what's there now. So I have some uncertainty about that. So I have uncertainty about how much I have to deliver to C. And just to make it, to give it some breadth of the distribution, I'll say it could either be 1 or it could be 7. So these others I know are all 2. I know that I need whatever 2,000 gallons in each of these, or 200,000 liters in each of these places. So I have so many liters that I have to deliver to each of them. And for C, though, I don't know exactly. It could be 100,000 liters, or it could be 700,000. I don't know which it is. Now, the problem is that my truck can only hold up to 10 of these units. So it only holds whatever 10. Let's say it's thousands, so 10,000 liters. So it only holds 10,000 liters, whereas these have some variation of that. So if I filled it up with 10,000 and I went out here and I delivered 2,000 here and 7,000 here, I'd only have 1,000 left, and I wouldn't be able to deliver to B. So then I'd have to go back and refill the truck, and then go back here and top off B, and then go over to A and go back to the depot. So the question is, how would you route the truck? Let's say there's a cost to going to D, a cost to going to C, a cost to B, A, and back. Given the cost that it takes to get to each of these places, what's the minimum cost way in which I should route the truck such that I minimize the total cost of delivering to all of the different places here? Now you notice if this could be 1 or 7, then on average it's 4. All right, so on average this is 4, and my vehicle holds 10. So on average I could go from D to C to B to A and then back, and I don't have to make 2 trips. So on average I can just do 1 trip. So if I solve the average problem, my average problem is I'll just go A, B, C, D, and back, or D, C, B, A, and back. And so I'd know exactly how I would do it on average. But if C is 1 or 7, or if C is 7, then I'm going to have to make 2 trips. So then I'd have some decision to make. Okay. Now, the expected value solution is that I go either A, B, C, D, or D, C, B, A. Either one is okay. But the expected value solution, either way I go, if I look at what actually happens with it, for example, suppose I'm doing A, B, and then I get to C, and C's value is 7. Then what I'm going to have to do is to go, I'll fill up as much as I can. I have 6 left, so I'll fill 6 out of C's 7 requirement. Then I'll go back to the depot, and I'll get an extra 1,000 gallons or 1,000 liters, go back to C, fill what was left, and then go to D and come back. Right? So if I do this A, B, C, D, I'm going to have to go A, B, C, then come back, then go back to C, fill it back up, go to D, and then return. So it depends on whether so I think that's the better way to do it. Yeah, I think that's the better way to do it. If I did it this way, I go to D, I go to C, and then I would decide whether I went to B and gave B a little bit and went back, or whether I just came back from C and then went back to B. So depending on which direction I go, whether I go A, B, C, D, or D, C, B, A, the expected cost of doing that, of using that solution A, B, C, D, or D, C, B, A, is either 14 or 13 and a half. So my expected cost of going around is either 14 or 13 and a half. Well, it turns out if I solve the recourse problem here, if I minimize the expected cost is actually minimized by first going to C. Because if I first go to C, I'll discover how much I have to deliver to C, and then I can make a decision about where I go next. So if I first go to C, well, let's say it was 7. I know I can deliver to B, so I deliver to B, and then I can go back, and now I have now I just have 2 closer places instead of having to go back to one of these, B or C. So now I just have 2 close places to visit. So it's better to go to C first, then go to B, and then if I have to go back, I'll go back, but then I'll just have to go to the close places and return. So the stochastic solution has a completely different approach. It goes first to the place that's furthest, but where I get to realize what the uncertainty is. So I want to discover what the uncertainty is first. So the stochastic solution does that at the very beginning. It goes out here, discover what this is, then while I'm out here, I can now take care of this distant gasoline station as well, and then go back to the depot. So that means that the recourse solution has an expected cost of 12 and a half. But that solution of going up to C and B and then A and then D and back, that's never optimal for any deterministic problem again. There's no deterministic set of values that is ever going to give me a solution that looks like that. Because it's not it's clearly not a traveling salesman kind of solution. Because I'm going up here and I'm crossing over before I get back to the beginning. So there's no deterministic solution that can ever reproduce this kind of behavior. It's behavior that's information seeking, whereas any deterministic solution, all the information is there. So you never have that kind of characteristic where you search for the information first before you make your decisions about where to go next. Okay, so this allows me to calculate the value of information and the value of the model. So in this case, so for information, think about I was solving a problem like this. I was minimizing the cost of whatever I have initially, maybe to set up the trucks, and then the cost of, this would be like the expected cost of delivering, or this is the cost of delivering under a given scenario solution. So the wait and see solution would be if I get to observe what that demand was, and then I get to make my decision, what would I do? So given that I could observe what it is, I could make my decision about where to go. And then I would go to C and B and then come back, like if it was a high demand. So I've represented that here by this. It's saying Z is the value of making decision X if the outcome is C. And what I'd like to do is, what I want to do is to minimize the cost over X of the expectation of Z of X and C. Well, if I get to see that actual demand before I make my decision, that's this wait and see solution. So this is where I get to see the demand before I make my decision. So I've observed the demand and then I make my decision X. So I'm minimizing X given that I already see what that decision is. If I take the expectation over that, in this routing problem, that gives me a value of 12. But as I said, if I solve the recourse problem where I make my decision not knowing, but only minimizing the expectation of this value up here, which would be the expectation of how much I'm going to pay for routing, given the uncertainty. Okay, so my recourse function value is 12.5. Wait and see value is 12. What that means is my expected value of perfect information is the difference between recourse and wait and see. So that's 1/2 in this case. So let's say this would be $1,000, say. Okay, so that's $500. That's my expected value of perfect information. But that mean value problem, which I called here the expected value problem, that was where I made a decision based on the expectation of the demand. So based on like that 4 as the expectation of what that demand would be at C. So that value, if I had solved that routing problem with the expected demand, that would give me a value of 10. So that would be much less than the recourse problem value, which was 12.5. But if I implement that solution, then I got this value that was either 14 or 13.5. So that means that if I use the mean value problem, use the deterministic problem, and I implement it, the value of implementing it, which I call here the expected value of the expected value problem, so a double EV, the value of that expected value problem is either 14 or 13.5. So that's much worse than what I get in this problem here. So when I take that expected value, I'm either 1.5 or 1 above the recourse problem value. So let's say this would be $1,500 or $1,000 versus $500. So the value of the model in this case is either 2 or 3 times the value of information. So it's worth more to solve the model than it is to discover what the demand is. So the model has more value than the demand. Now there are certain relationships that this expected value of perfect information and the value of the stochastic solution, they have certain properties. They're always non-negative, so the value of each of them is always positive. The value of each of them is bounded above by the difference between the expectation of the expected value solution minus the expected value solution. So in this case, this would be the 14 or 13.5 minus 10. So they're always, we know that they can be no bigger than 4 or 3.5. So both of them are bounded above by that. So if these values are 0, then both of these are 0. So there are cases where this value is 0, and then that means the value of information is 0 and the value of the model is 0. So in some cases, you solve the mean value problem and you get the solution. Get a solution that is good for all of the possible scenarios, or good when I consider the scenario as an expectation. So sometimes both of these are 0, but most of the time both of them are positive, and it's possible that they can be very different. That is, that one of them can be 0 and the other isn't. So it's possible that information value is 0, but solving the right model is worth a lot. Or it's possible that the model isn't worth very much, but if I knew the exact information, then that would be worth something. Okay. Now there are other ways you can bound this information value, and here these should be less than or equal to down here. I've set it up as what I call the pairs problem. You can take, instead of one scenario at a time, you take 2 scenarios. What I call the pairs problem. Take 2 scenarios and put them together into a model. And then I'll solve a model where I take one of those scenarios as a reference scenario and combine it with another scenario. So I'm minimizing the cost of the current cost plus a combination of 2 scenarios in the future. One called my reference scenario and one other scenario. And I make sure that they meet, each of them meets the constraints, so they meet the future constraints. And again, I have non-negative variables. If I combine these reference scenarios together, I call that the sum of the pairs problem. And then I can take the value of those reference scenarios and the expected value of using the reference scenarios. And then I can get bounds on the value of the stochastic solution. So I can use these reference scenarios to give me bounds on the value of the stochastic solution. So this should be less than or equal to. So the value of the stochastic solution is less than or equal to the expected value of using the reference scenarios minus this combination of the reference scenarios. So that's some combination of the reference scenarios that goes in here. And it's always going to be bounded above by this expected value of the reference scenario minus if I use the reference scenarios. Yeah. Well, this is the common thing that most people do is they take all the random variables and substitute the mean.
So basically they are mean scenarios.
Yeah, just solve with the mean.
So then it becomes deterministic.
Then it's a deterministic. So this is the deterministic model. And this is, I use the solution of the deterministic model, but now I realize the random variables, and I see how much that's worth when I use that solution.
But the minimum values increase when you do that.
Yeah, because this is, I take the solution that I get from here, but now I apply it where these are no longer just the mean, but they have all the different possibilities. So now that they have different possibilities, what value do I get?
What when if that value has increased when you do the EEV, my expectation of then my actual problem is better to take that average scenario because that's less.
Yeah. You're always better. So this would be if I use the solution that comes from the deterministic model, this is what I'll get in reality, whereas the 12 and a half is what I get when I solve the stochastic program. That's the RP. That was on the previous slide. The RP is 12 and a half. Yeah, the recourse problem is I minimize x of the expectation. Yeah, and this one I take the,
Solving the mean value problem, and you already have the lowest minimum value.
Oh, well, this is not, I mean, this is not implementable because it means that the only thing you get is the mean. The only value that occurs is the mean.
So by doing so, does it mean that we change the nature of the model?
Yeah. I mean, this is assuming that there's no uncertainty, that I only get the mean. Like I would only have the mean yield, or I only have the mean demand. Yeah, so if you only have the mean, you get something that's very biased, always biased low in terms of cost. So it's because it's so biased, in reality, if you use that solution, you'll get something much worse. If you use that solution, you'll always get something much worse. Yeah, so that difference kind of bounds your information value, but it also bounds your model value. Okay, now the Paris problem is just another way to bound it. Okay, let's look at so this is the kind of formally describing these models. So there are decisions now, observe an uncertain outcome, and then take a recourse action. So I've got decision now, recourse action in the future, and then this is my recourse function value again. Again, everything here was t was where the randomness occurs. Now I also might have, like in the financial planning model, I have decisions that are made over time. So those are these multi-stage models. One way in which I could describe those models is I'd say there's a value from going from decision at one point in time, or a state at one point in time, to a state at a different point in time. And I get value, or I get utility out of going from one state to another, or being in a single state, coming from a different past state. And I take that value over time, then time could go up to infinity. And that would give me this dynamic. I can set up my dynamic model just like this. Minimize the expectation of all of these future values from transitions from one state to another. I can also represent that in the dynamic program or in the Bellman equation format, which says that the value at any point in time in a given state for a given action, or let's say this is a given state of wealth, say. Wealth is here W, and X is an action, like investment. That action, or this might be my state. My state might be how much I have invested in the risky asset, how much my wealth is. And then I minimize over the investment that I make in this period, the costs in the current period, plus my expected value of being in future states. So this might be, okay, what future state am I going to be in terms of my investments? What future state am I going to be in terms of wealth? And I take my expected value of those future states. So it's a way to describe this, the dynamics of one period plus all the periods together in kind of a compact format that is the single period right now plus the expected value of everything in the future.
One thing I want to ask you here, go back to this. I see problems in growth theory, macroeconomics, use a form like this summation equal to 1 to infinity expectation of this.
Yes.
But how do they always actually that kind of thing to convert? You can actually do that here, apply whichever condition they will do term by term differentiation and all this.
Yeah, so either you have explicit assumption that the growth is limited to something that will give you a finite value, or you show that there are conditions under which you always get a finite value. But you have to show something, because this isn't going to be finite naturally. So you'll have to have some kind of condition about the growth and discounting that will give you a finite value. Yeah, so there's got to be either it's explicit assumption or you show that it's because of the conditions of the model that you'll always get a finite value. Okay, so basic modeling questions are, when is a model consistent? What form should an objective be? And the constraints, and what, maybe do I have to assume something about the distribution? So those are the things to consider in building these models. So one thing about, so consistency should be that you don't allow the model to give you an answer that you know contradicts reality. So if it gives you something that's not, it's sort of provably not real, then that's not consistent. So for example, it's like a financial model should not allow arbitrage. It's kind of like a physical model should not allow to continually gain energy without putting energy in. So the same thing is true for a financial model. I can't make money if I don't put money into it without taking on risk. So you shouldn't be able, perpetual motion. You can't keep on gaining energy without putting energy in. Okay, so a financial model should not allow arbitrage. So there shouldn't be a way in which I could buy and sell and make an infinite amount of money by trading in something. So for example, here's a model that is going to end up with arbitrage, but it doesn't look obvious at the beginning. So sometimes these arbitrage situations are not completely obvious, but they're inherent in the model. So here's a problem where I have a price of a share of stock is $1. The risk-free rate, say, is 10%. The stock can either go to 1/2. My model says the stock either goes to 1/2 or 2, and each of them happens with equal probability. So it starts at $1, could go to 50 cents, or it can go to $2. Each of them happens equally. And there's a call option that has a value of $1.50 when the exercise, or it has an exercise price of $1.50, and its value is 20 cents. So that means the call option says I'm able to sell the stock at $1.50 in the future. So if the stock's price is $2, the call option is worth 50 cents. If the stock's price is 50 cents, the call option is worth 0. So the call option is either worth 50 cents in this outcome or 0 in the other outcome. This one happens with probability 1/2. So with probability 1/2, it's worth 50 cents. If it was just straight expected value, it would be 50 cents times 1/2, it'd be 25 cents, and I'm saying it's available for 20 cents, so it sounds like that should be reasonable. It looks like there isn't obvious arbitrage. But in reality, this model actually has arbitrage. And let's say I maximize the value of the portfolio at time 1. But I put in some downside risk. So I say, oh, I don't want to lose any more than a certain amount of money. Okay, so my decisions are, in the first stage, I'm going to invest a certain amount in the stock, a certain amount in a bond, and a certain amount in buying these call options. And now my price is, I'm indicating here by A. My wealth, say, is B, so I can invest B. And I can only invest up to, or I have to invest at least L. So L is a lower bound, and U is an upper bound on my investments. And my returns are represented here by C, and the probability of each scenario is S, PS. So my decisions are the wealth under a given scenario, and then how much am I below my, how much am I below a target, since that this was my risk limit. So I have a target to achieve, and then, yeah, if I'm below the target, I get a penalty. That's what I'm minimizing. So I'm minimizing the penalty of being below that, being above the target. Okay, so here's my, so I minimize, yeah, W is that I'm above my target. W is my wealth. Yeah, so if my wealth is above the, yeah, or basically I'm maximizing wealth, maximizing my expected wealth, so minimizing negative expected wealth. So I maximize expected wealth, I invest everything, I have, so this is invest everything, then I get my wealth back in the future from these different returns. And then if my wealth is above the target, I don't need to have any penalty. But if my wealth is below the target, then I'm constrained that my expected value is less than this risk. So I solve with an upper bound on each of the assets, and I limit this downside risk so that the loss, let's say below whatever the bond returns, is less than 10 cents in expectation. So I solve this problem. I set it up like this. This is wealth in scenario 1, wealth in scenario 2. This is the cost at the very beginning. This is what I get in scenario 1. This is what I would get in scenario 2, and then this is the limit on the risk. I solve this model and I get a solution that looks like this. I invest, this is the stock, so this is the bond, and this is the call. So I've sold several call options. So I've sold to someone else these call options. I've borrowed money. These cost 20 cents each, so I sold these. I got 90 cents. I borrowed some money here. I invested over here. Yeah, so I actually didn't put anything into this. So I was able to sell some of these, borrow here, place it into the stock. All of those are going to use up my budget constraint. My budget was actually nothing. And then this is what happens in the future. High price is either $2 for the bond or 50 cents. The bond goes up by 10% no matter what. The call is worth 50 cents or 0. And then, am I above? Well, in this case, I'm above, so I get this back. Am I below? Oh, in this case, I'm below. I get that back. My expected value here is 0.09. My expected downside risk is below my target. But what's actually happened is if I had increased the amount of this share, I would just keep on increasing how much I invest, how much I borrow, and how much I sell these bonds. And I'd keep on increasing my expectation, even though I didn't actually put any money into this. So as I increase that downside limit, I would just increase the overall investment. I wouldn't change anything else about this model. So it sort of suggests that I'm taking bigger and bigger risks, but the model's not telling me not to do anything. The problem is that this model has what I call a hidden arbitrage. That I don't have prices that are consistent with each other. So the prices allow me to create a model in which I think I can make an infinite amount of money, but I know in reality I can't. So common causes for this is that I have stale prices, or I didn't include transaction costs that are all actually there, or I didn't include that the market might react to what I did, or I just don't have correct prices. By putting in constraints, sometimes you mask that. So the constraints often make it less obvious that there's arbitrage in the model. But linear programs in particular are going to go to extreme points. So the fact that you have extreme point solutions means if there's any kind of arbitrage, you're probably going to exploit it in your models. So models, particularly linear models, often are going to exploit arbitrages, but arbitrages shouldn't be there. Often what people do in practice, they may put arbitrage into their model, and then they try to take it out by putting in some constraint. But the constraint is just eliminating the arbitrage. It's not dealing with the fact that you should have had different prices at the very beginning. So probably your model is not well constructed. So the model is not well constructed because it has prices that don't agree with one another. So this downside risk constraint, a constraint might mask what's going on in the model, and it prevents you from seeing that there's actually an arbitrage. So you might not, often you'll see an arbitrage that your model will say, oh, I have an unbounded solution. Unbounded solution means there's some kind of arbitrage. But if you put in too many constraints, you don't see unbounded solutions. So you don't see your model says, oh, I have an unbounded solution. But in reality, you have an unbounded, you would have had an unbounded solution if I eliminated that constraint. So if I had eliminated this downside risk constraint, I would have seen that there was actual arbitrage in that model. Okay, so this is that having a downside risk constraint like that maybe was not the best choice. There are other things that you can do. One is to put it into your utility function, put it into your objective. So have expected utility that includes risk into your objective. Or you try to make your preference depend somehow probabilistically on the outcome. So make sure that I do the best stochastically relative to some other outcome. So I'll consider relative to a benchmark and try to be stochastically better than the benchmark. Or to be better than the benchmark with a certain probability. Or, again, worst case, like in robust. Just about robust. So most of the time in stochastic programming, we solve models like this. I minimize the expectation of x. I take the expected value of some function that depends on a probability measure where that probability is known. I know how I can assign probabilities to the set of outcomes. Uh-huh. Oh, you mean why this is? I mean, this is stochastic here. This, oh, you mean whether you replace it with a deterministic? Yeah, then you have a deterministic model. Well, if you can take the expectation. Right. Yes. Yeah, yeah. Yeah, so, so I think it's, I mean, I think of this as stochastic optimization. But yeah, you can replace it with a deterministic function of x. And now it becomes deterministic optimization. But it's a different function. But it's if you can do it, yeah. So most of the time, we can't do this explicitly. We have to do it approximately. Yeah, that it could be. Yeah, but it has something different because it's, you take the expected value here. Okay, so stochastic programming is in this framework that it's expected utility, and you're optimizing over expected utility. Yeah, but it's a question of what is your utility. So this this f here, that's your utility given your action and given the uncertain outcomes. And I'm saying that I can measure that. I know what my utility is, and I know what this distribution is. So stochastic programming, you're assuming that we know what these things are. In robust optimization, you're saying there's a function here that relates my action and these set of possible outcomes, and I take the worst case over all the possible outcomes. All possible outcomes in some uncertainty set. So I take the worst possible case over here, and I minimize for x in that worst possible case. The worst possible case is called, in robust optimization, that's called the uncertainty set. So it's the uncertainty set over here of the set of possible outcomes. Now, the reason I put G over here, I put G over here because it's possible that you can make these consistent if you think that this G is different from this F. That the objective over here might be different from the objective that you would have with expected utility optimization. That is, it may not be that I'm thinking with the same kind of future values when I look at it from a robust optimization perspective as when I look at it from the stochastic optimization perspective. So you could think of it in the robust optimization could somehow be the same as expected utility optimization, but your function here is not necessarily the same as the function over here. So I think, yeah, so when often people talk about this as being a completely different model, it's possible that these two models are actually the same, but I have a different form of G. So that's kind of the point of this. Okay, so the same thing occurs with models with probabilistic constraints. So models with probabilistic or chance-constrained models are models with probabilistic constraints. So my advisor was George Danzig, he's the one that came up with the recourse models. The people that came up with the chance-constrained models were Charnes and Cooper. Cooper just died last year, I think. Charnes died a while before that. So they didn't get along with Danzig. So there's, yeah. I once asked the two of them to speak together. So I knew that they had had bad blood before, and I thought that was, like 30 years prior to that. And I thought 30 years should be enough, that these things would go away. And so I invited them to speak in the same session, and Charnes was to speak first, and then Danzig. So Charnes gets up and says, "Thank you for inviting me. My student will now give my talk." And then he sits down, and his student comes up, and she gives the talk. And then, so then Danzig comes up, and he says, you know, some days are really good days. And other days, you wake up and you learn you're supposed to speak after Abraham turns. And then he goes on and gives his talk. But anyway, Charles and Cooper came up with this. That's supposed to be less than or equal to. Okay, so this I've put this probability in here. So this is like the reliability. This is saying the chance of meeting my demand is at least alpha. Instead of having a penalty if I don't meet my demand, I just say the chance of meeting the demand is at least alpha. Okay, so that's the chance constraint form. The chance constraint can actually be the same as robust optimization if my uncertainty set is a set that has probability alpha. And then I say that my G function is F everywhere that the constraint is met, and it's, let's say, 0 everywhere else, then this is the worst thing that happens with a given probability. So the worst thing that happens in the case of a set of probability alpha. So I have an F that I optimize given that with anything that happens in this set of probability alpha, I get if
But delta is operating, when you get a function is operating on which variable?
it's operating on C. Yes, right. Yeah. So if I
Here, here what is happening is acting on some
yeah, it's on
it is I or
no, it's on X. On X. Yeah, X.
so it is acting on
Acting on X. It's on
here also is acting on X.
on X. Yeah, yeah. So it's acting on X. So it's on X, such that the expected utility is. So I'll pay if I was an expected utility where I would pay 0. I would pay if X does not satisfy. Whoops. My cost. I must meet my constraint. So I think it's f of x plus this delta. Should be plus. So I'll pay f of x if I have an x such that the probability of h being h of x and c being less or equal to 0 is at least alpha. And I think that's the same as if the robust optimization, that my G is a G such that it's infinite if I choose any C that gives me a value, a probability that's less than alpha. Okay, so the point of this is that by redefining what your objective is, you can actually transform these problems from one to another. And you could also think about it as a competitor, like there's a competitor that chooses an action to take in response to your action, and to the the outcome. So if you have a competitor, the competitor gets to choose what action to take for each of the possible outcomes. Then like your competitor can choose the worst case for you for every possible realization within this uncertainty set. Or your competitor can choose your competitor can choose in reaction to you and whatever the action is that you might take. So a way to look at it is, if you think about it in this sort of game framework, expected utility optimization means that your competitor is kind of irrelevant, whereas robust optimization assumes that your competitor is perfect. They're always kind of giving you the worst possible case for anything that you do. Okay. All right, so in this, what I tried to show is that stochastic programs obtain solutions that approaches based on static models. You can think of static as like just planning one period for the next, that they cannot, because they allow you to adapt. And that's something that these static models are not capable of. The value of information and the value of the model are limited by the difference between the expectation of using the expected value solution. So if I take that and I compare it to the expected value solution, so this one is like a high cost. This is the low cost, biased, low cost. They're both limited by that, but they vary independently. So one can be high and the other can be high or low. So they have different values. So sometimes you get more from model, sometimes more from information. And in terms of models, one of the important things is to make sure that your models avoid arbitrage. So make sure that the arbitrage is removed from these models in order to be able to come up with consistent choices that can actually be used in practice. So eliminating arbitrage is a necessary condition. Okay. Well, thank you for today. Yes.
in dynamic optimization. So, is the Bellman equation given the necessary and sufficient condition for the optimality?
Well, yeah. The Bellman equation, if you solve the Bellman equation, that is necessary and sufficient. For household utility? Yes, yeah, you could solve that for any kind of. Solve it manually. Well, it depends. For very small problems, yes. But usually you have to reduce it down to very small, very low dimension to be able to solve it by analytically. Yeah. If you can reduce the dimension, then you can solve it. Yeah. But otherwise, yeah. Thank you.